Welcome to JB's Academy of Science. In this lesson, we are going to learn about electrostatic potential energy, electric potential due to a point charge, electric potential due to a dipole, potential due to a system of charges, and problems based on electric potential. So before going to electrostatic potential energy, let us recollect the concept of potential energy. So we have studied about gravitational potential energy in our earlier classes. So the energy possessed by a body due to its position with respect to the position of another object is called potential energy. Now, for example, if you consider a mass, an object of mass m is placed at a height h from the surface of the earth, we know that it will possess a potential energy Pe is equal to mgh, where m is mass of the object, g is the acceleration due to gravity, and h is the height of the object from the surface of the earth. So in the gravitational field of earth, if an object is placed at a point, it will possess an energy which is called gravitational potential energy. And this energy depends on the height of the object from the surface of the earth. Means it changes from place to place with the height, or it depends on the position of the object. Similar way, if a charge is placed in an electric field of another charge, it will possess an energy, potential energy, called electrostatic potential energy. The energy possessed by a charge placed in an electric field is called electrostatic potential energy. So here consider a charge plus Q, capital Q. Now consider a point P in the electric field of the charge Q. We are placing another charge, small q, at the point P. Now, this small q charge will possess certain amount of potential energy due to the presence of the charge capital Q. So this energy possessed by the charge which is placed at this point P is electrostatic potential energy. It can also be defined as the work done to bring a charge from infinity to a point in an electric field. This work done is stored in the charge as potential energy. This is called electrostatic potential energy. For example, if you bring the charge small q from infinity, that means from outside the field, to the point P, what is the work done in bringing this charge? That is equal to the electrostatic potential energy of the charge. The unit of electrostatic potential energy is joule. It is nothing but energy. So the unit of energy is joule. Now, electrostatic potential. Now we studied the concept of electrostatic potential energy. Now what is electric potential or electrostatic potential? We know that the charge Q placed at the point P will possess some amount of energy. We called it as electrostatic potential energy. Let U be the electrostatic potential energy of the charge Q placed at the point P. Then the energy possessed by unit positive charge placed at the point P is U divided by Q. U is the total energy of Q charge. Then the energy per unit charge is U divided by Q. This we call electrostatic potential or electric potential. The unit of electric potential is joule per coulomb. or volt. 1 joule per coulomb is known as 1 volt. Now, again, similar to the definition of the electric potential energy, here electric potential we can define electric potential at a point in an electric field is defined as the work done in bringing unity positive charge from infinity to the point. So consider a charge plus Q. Consider a point P in the electric field of the charge. We are bringing unity positive charge from infinity to this point. Now, the work done in bringing this unity positive charge from infinity to this point P is the electric potential or electrostatic potential at the point P. Remember, electric potential energy unit is joule. Electric potential unit is joule per coulomb or volt. Now, electric potential difference. Now, consider the electric field of the charge Q. Let A and B be two different points in the electric field. Now, we are moving 1 coulomb charge, that is unit positive charge, from one point to another point, from A to B. Say, from A to B, we are moving this charge. Now, this work done in moving this charge from A to B or from one point to another point in an electric field is called electric potential difference. Electric potential difference. So, it is the work done in moving a unity positive charge from one point to the other point. Here, potential at A, let us take VA, and potential at B, let us take VB. These are electric potentials at A and B separately. Now, potential difference between A and B is VAB, difference in the potentials, VB minus VA. Remember, electric potential is a scalar quantity because it is charge per coulomb, energy per unit charge. Energy is scalar quantity, charge is scalar quantity. So, electric potential is also a scalar quantity. Now, let us discuss electric potential due to a point charge. So, consider a point charge plus Q. Consider a point charge plus Q placed at the point O. Consider a point P which is at a distance R from the point O or from the charge. Consider a point A where unit positive charge is placed. 1 coulomb charge is placed at A. Now, this point A is at a distance x from the charge. Now, electric field at A due to the charge Q is equal to 1 by 4 pi epsilon 0 Q divided by x square. That is the electric field at A. Now, the force on 1 coulomb charge placed at A, we know that F is equal to Q into E. So, 1 into E, it is again equal to electric field. Now, this 1 coulomb charge, we are moving through a small distance dx towards the charge from A to B. Now, a small work is required to move the charge from A to B. This small work done in moving 1 coulomb charge through a small distance dx from A to B. dW is equal to minus E dot dx. Force into distance is work. So here force on 1 coulomb charge is E. Therefore, dW is equal to minus E vector dot dx vector. Here work is done against the electrical forces. So it is negative. That is dw is equal to minus 1 by 4 pi epsilon 0 q divided by x square into dx. We are substituting for E. Now, we know the small work in moving the charge through a small distance dx. Now the whole work done in moving the charge from infinity to the point P, that is given by integrating the small work, that is W is equal to minus integrate E dx within the limits of infinity to R, or W is equal to minus integrate infinity to R q by 4 pi epsilon 0 1 by x square dx. So integral of 1 by 4 pi epsilon 0 q by x square dx. So here q by 4 pi epsilon 0 is a constant. So we can take it outside the integral. So this is equal to minus 1 by 4 pi epsilon 0 q integral infinity to r 1 by x square dx. 1 by x square integral is minus 1 by x. So minus and minus becomes plus. So 1 by 4 pi epsilon 0 q into 1 by x within the limits infinity to r. Applying the limits, W, the whole work done, is equal to 1 by 4 pi epsilon 0 divided by, V is equal to 1 by 4 pi epsilon 0 into Q by R. Because the work done in bringing the charge from infinity to this point P is nothing but electric potential. So V is equal to 1 by 4 pi epsilon 0 Q by R. Now, electric potential due to an electric dipole. So here you consider an electric dipole with charges plus q and minus q placed at A and B as shown in the figure. Let O be the center of the dipole. Consider a point P at a distance r from the center of the dipole O. Let R1 be the distance of the distance of the point P from charge plus Q, and R2 be the distance of the point P from the charge minus Q. Okay. Now, the electric potential at P due to this dipole AB is to be determined. So here we can find out potentials due to individual charges at P. Plus Q will produce its own potential, minus Q will produce its own potential. Now, the potential at P due to the charges plus Q and minus Q are V plus Q is equal to 1 by 4 pi epsilon 0 Q by R1. V minus Q is equal to minus 1 by 4 pi epsilon 0 Q by R2. These are the potentials. Now, the net potential V is equal to V plus Q plus V minus Q. That is 1 by 4 pi epsilon 0 Q by R1 minus 1 by 4 pi epsilon 0 Q by R2. So V is equal to 1 by 4 pi epsilon 0 Q into 1 by R1 minus 1 by R2. Now our aim is to find out what is R1 and R2. Look at this figure again. Now from triangle ADO, DO is equal to A cos theta, and from triangle BCO, CO is equal to A cos theta, where 2A is the length of the dipole. So A is half the length of the dipole. So PD is equal to OP plus OD, that is R plus A cos theta. PC is equal to OP minus OP, that is R minus A cos theta. Now, R1 is nearly equal to R minus A cos theta, and R2 is nearly equal to R plus A cos theta, provided R is much larger than A. Then this equation becomes V is equal to 1 by 4 pi epsilon 0 Q into 1 by R minus A cos theta minus 1 by R plus A cos theta. Just we are substituting for R1 and R2. On simplifying, V is equal to 1 by 4 pi epsilon 0 Q into 2A cos theta by R square minus A square cos square theta. But we know that the dipole moment P is equal to Q into 2A. So Q into 2A we can replace with P. This equation becomes V is equal to 1 by 4 pi epsilon 0 P cos theta divided by R square minus A square cos square theta. For R much larger than A, R square minus A square cos square theta is nearly equal to R square. So V is equal to 1 by 4 pi epsilon 0 P cos theta divided by R square. So this is the electric potential due to a dipole at any point around the dipole. Now let us consider some special cases. One is if the point P is on the axis of the dipole, then theta is equal to 0 or 180 degree. Then cos theta is plus or minus 1. So we can substitute the value here. It is 1 by 4 pi epsilon 0 P by R square. V is equal to 1 by 4 pi epsilon 0 P divided by R square. This is if the point is on the side of the positive charge. Or V is equal to minus 1 by 4 pi epsilon 0 P by R square if P is on the side of the negative charge. Second case, if the point is on the line perpendicular to the axis, that is the perpendicular bisector, equatorial line, then theta becomes 90 degree, then cos theta is 0, then the potential is 0. Remember here, the potential at any point on the equatorial line, that is the perpendicular bisector of an electric dipole, is always 0. Now, electric potential due to a system of charges. So if there are a number of charges in a system, let us say Q1, Q2, Q3, Q4, Q5, the net potential at a point due to all these charges, let us calculate. So look at the picture. Consider a point P. Consider the charges Q1, Q2, Q3, Q4 and Q5. Let R1P, R2P, R3P, R4P, R5P be the distances of the charges from the point P respectively. Now, let V1, V2, V3, V4 and V5 be the potentials due to the charges Q1, Q2, Q3, Q4 and Q5. Then, potential being a scalar quantity, the net potential is just the algebraic sum of the individual potentials. So, V is equal to V1 plus V2 plus V3 plus V4 plus V5. That is 1 by 4 pi epsilon 0 Q1 by R1P plus 1 by 4 pi epsilon 0 Q2 divided by R2P plus etc. 1 by 4 pi epsilon 0 Q5 divided by R5P. We can take 1 by 4 pi epsilon 0 outside. So V is equal to 1 by 4 pi epsilon 0 Q1 by R1P plus Q2 by R2P plus Q3 by R3P plus Q4 divided by R4P plus Q5 divided by R5P. Now, if there are n charges in the system, then we can just replace all the summation with the sigma notation. V is equal to 1 by 4 pi epsilon 0 sigma I is equal to 1 to n qi divided by rip. So this is the potential due to a system of charges. Now let us discuss some problems based on the concept electric potential. 2-point charges 12 microcoulomb and minus 6 microcoulomb are placed 20 centimeter apart from each other. Find the point between them where the net electric potential is 0. So here 2-point charges 12 microcoulomb and minus 10 microcoulomb minus 6 microcoulomb are kept 20 centimeter apart from each other. Consider the point P where net potential is 0. Let x be the distance of the point P from 12 microcoulomb charge. Then distance of the point P from 6 microcoulomb charge is 0.2 minus 6. Sorry, 0.2 minus x. For the potential to be 0, V1 minus V2 is 0. That is, negative charge produces negative potential. V1 plus V2 is 0, but V2 is minus. So V1 minus V2 is 0. That is 1 by 4 pi epsilon 0, 12 into 10 to the power of minus 6 divided by x minus 1 by 4 pi epsilon 0, 6 into 10 to the power of minus 6 divided by 0.2 minus x is equal to 0. Now, simplifying, 12 by x is equal to 6 divided by 0.2 minus x, or 2 by x is equal to 1 by 0.2 minus x. Solving for x, we get x is equal to 0.13, that is 13 centimeter from the 12 microcoulomb charge. Charges of 10 microcoulomb are placed at each of the vertices of a regular hexagon of sides 20 centimeter. Find the electric potential at the center of the hexagon. A regular hexagon, 10 microcoulomb charges are kept at each of the vertices. What is the electric potential at the center? So V1 is equal to 1 by 4 pi epsilon 0, 10 into 10 to the power of minus 6 divided by 0.2. That is potential due to one charge. Now there are 6 corners, 6 charges are placed at 6 vertices. Therefore, the net potential is 6 times the V1. So V is equal to 6 into V1. That is 6 into 9 to the 10 to the power of 9 into 10 to the power of minus 6 divided by 0.2. That is 2.7 into 10 to the power of 6 volts. That is the net potential at the center of the hexagon. More problems will be solved in a separate video. Thanks for watching the video. If you think the videos are useful, please subscribe and support, and also mention your valuable suggestions and opinions in the comment section. It will help us for improving our video quality and the requirement of the content to be presented in the video. Thank you.